Hi and welcome everybody to Rudy's Electronics Lab. And I'm quite excited today to talk about a project I've been working on for the last couple of months, and it's in the context of bit error rate testing, BER testing. And I made already a couple of videos that I posted on that recently where I talked about the purpose of BER testing and also about the question whether I should use like a device already got around the lab to create the right type of pseudo-random signals, the PN9 signals I'm interested in, or build something myself basically. And one of my earlier videos I looked into that and I came to the conclusion that it would be interesting and also fun to build a PN9 generator myself. And in this video I'm going to actually show that, that device and talk a little bit about the design choices that I made. And the device actually is right over here. This is the new BER tester I've been working on, and I take it a little bit closer to the camera here. You can see here that it got like a couple of different outputs. I'm going to talk about that. It got like a menu system that you can go through a number of different bit error rate scenarios. It got an internal clock as well as an external clock here, and we're going to go in greater detail in its design. But I'll also be sharing the hardware design as well as the software code, so you can also build this yourself. And one of the nice things about it, I think, is that in the end you can build this BER tester for a bill of material of less than 50 euros. So it's also quite affordable device, I would say. But let's go talk a little bit about how it works and the different things that I've been running into when I've been making this device. Now, in my earlier video I already said a little bit how my ideal NP9 signal generator would look like. And that would be one that would create a proper NP9 sequence as well as modified sequences where I can introduce errors, pre-programmed errors in certain ways. And ideally it would also output these proper and modified signals at the same time. I would appreciate to have some additional outputs on the device, including a clock output, a signal when the frame starts, so you see exactly when the 911 bits of an NP9 sequence start, and also an error bit that will show you the difference between the proper code and when the modified code has an error in there. So you would see a flag that there will be an error going on. And it will be a device, my ideal device, that would create a PN9 code, so that's 511 bits length. I could also think about PN11 or PN15, longer pseudo-random codes, but I don't really need that right now. What I kind of care less about will be the speed of the device, what the clock speed will be by which the signals come out, and the clock stability, like the drift or the jitter of the thing. Now, honestly, when I started building the device, I started to change my mind a little bit because speed started to matter more than I thought it would, and also clock stability was something that started to annoy me more and more. So eventually I also paid quite a bit of detail actually to get speed and clock stability up to higher standards than I was originally thinking about in my device. Now, the main topics I want to talk about in this video in terms of this prototype are the following ones. First of all, how do we create a proper set of NP9 pseudo-random bit code? Secondly, what microcontroller do we select to build our prototype with? And thirdly, how can we attain proper timing in the device? And then we're also going to talk a little bit about the final prototype, and we can see also a little bit of testing on it. Now, starting with the question how to create a proper PN9 code. And there are a number of different roads to go there. So some of them I considered is, first of all, use a piece of computer software and let it create the PN9 code for me, save them into a table or an array, and then play them back with the device. So one program you could use there in MATLAB. Actually, MATLAB has quite extensive functionalities to creating pseudo-random bit sequences. And right now I'm showing you some on the screen here. So there are plenty of options you can choose from. As you can see here, the one that I've selected is created from a shift register, the proper common way to make it in hardware, but you also see it how it's done here in software. So that's one option, right? Another option basically will be to write a bit of computer code, could be Python, could be C++, and integrate that into the device and have it created live, on the fly basically, calculating the code. Yet another option will be using such a computer code, but then offline create like the whole sequence we're interested in and save that again into a table or an array. And for both of these two options, I'm showing you now some example of people that have posted some code on the internet that's generating this type of NP9 codes. And finally, I could sample it from an existing instrument, just use something already got around and see what code comes out. Now, I've been playing around a little bit with these different options and not all of them were very easy. For example, I've been using option number 3, this Python code. I built it all, but eventually somehow my bit error tester did not think it was a proper NP9 code. So I was running into a couple of different troubles there, and long story short, I decided to sample something from an existing instrument, because I do have some instruments around the lab that create already PN9 code, and these instruments do work properly with the bit error rate tester that I'm using. They consider that as a totally perfect signal from their testing. So eventually I decided, let me go and take that existing signal that I got here, but let's try to capture that signal and get it into my prototype here. So what actually I've been doing, I've been sampling that instrument, and the instrument I'm using here is basically the Roden and Schwartz SMIQ signal generator. It's got a quite extensive section of creating NP9 signals, and it also can output a clock signal and a frame signal. So that makes it quite attractive basically for this exercise. Now, how we're going to go about and capture this signal? What I did is actually use a oscilloscope to do this capturing part. And well, most oscilloscopes, as you will know, have serial protocol decode, and many of them actually also have a parallel bus decode function. And it's the parallel bus decode function that allows you basically to do this type of capturing. So I took an oscilloscope and I connected the signal that I'm interested in, the clock that comes out of SMIQ, and the frame signal, and I inputted them in this case in a Roden and Schwartz RTB oscilloscope. So this is a little bit how the NP9 signal looks like. So you see the NP9 signal changing quite often at the top, and below that the second line in the graph here, basically you see when a new frame starts, a sequence start of 511 bits, and then we got the clock signal as well. Now, then we start to configure a parallel bus. I will not go in great detail here, but actually the parallel bus will be only like 2 different bits here, because we only need to sample the NP9 code and the frame rate code, and the clock signal basically will be used basically to clock the capturing process, basically to tell the oscilloscope when it has to clock a certain value out of that bus now. So you can all configure that here, and you can do that very well with the RTB oscilloscope, but also other oscilloscope, many of them will have similar type of function sets here. Now, I did run into a bit of a problem here that I want to talk a little bit about right now, and that was the timing of the signals coming out of the SMIQ. Because what comes out of the SMIQ basically looks like this: the clock signal, the data signal, and the frame signal. And I've magnified it a little bit from the earlier picture here. But what is exactly the problem that I'm having here? Well, with the clock signal, basically it is the positive edges that trigger the oscilloscope, like, okay, read that value and analyze what it is and go and put it into a table or so. Now, when it comes to the real signal I'm interested in, the data signal, the NP9 signal, we see there that signal is always stable and fine on the moment that the clock has a positive edge. It's either the 1 or the 0. Actually, the changes are at the clock going down, and I don't care about that. The system is triggered by a positive clock sequence here. So everything is fine here. However, if I want to capture the frame rate, what we do see here is that the frame rate goes positive exactly the same time as the clock signal. And sometimes the one signal arrives first and sometimes the other signal arrives first. So what I was analyzing this signal, and sometimes I get a sequence of 511 bits, that's correct. Sometimes I would get actually a sequence of 510 bits, and other times I would get a sequence of 512 bits. just because they happen to go up exactly at the same time. This is not necessarily a fault of the SMIQ. This is the way I think it was designed to be. But the way I want to use this clock signal basically to be able to capture also that frame bit, that's a bit of a problem. So the solution to that is actually introduce a little bit of delay into the frame signal. Into the clock signal, or come a little bit earlier, and that will basically solve the issue at hand. So after figuring out this problem, I started capturing a longer range. So I started capturing like a set of 511 bits. Actually, I captured a number of sets, like 5 or 6 sets, just to be able to make sure that each time I would getting exactly the same set, because that is the whole point about NP9 code. It's a predetermined pseudo-random bit which repeats itself exactly, and in my earlier video I went much more into detail on that. So I basically had the oscilloscope capturing 5 or 6 full frames for later analysis on a computer if they really respected all the proper characteristics of a NP9 code. And then on the computer I wanted really to see if the code was every time, you know, the same length and actually the same content. So in order to do that, I did that with a little program, one of my favorite text editors, BER it's called. On Windows computer, I think EDT is a pretty powerful plain text editor. And what you see here, and I even printed it out on a piece of paper, I analyzed that I exactly every time got 511 bits, but also every time I got exactly the same sequence. So now I just search on a shorter piece of string where you see the start of it, but if I would search on a longer piece of string, I would see that exactly the 512 bits are the same every time coming out. So this gives me some confidence that I probably have been able to capture the code that's coming out of my SMIQ device. I'll also be sharing this code. I'll be sharing the software code of this device and this PN9 sequence already in there, and I've already shared it on the EEV blog as well in the post, where you just see the bit codes, the 1 and the 0s, should you want to do some of your own projects along this line. Now, up to the next topic, and that is about selecting a microcontroller or a board basically that will be able to build my little project on. And I've been using Arduino platforms mostly in recent years, so I wanted to build upon the knowledge that I got from Arduinos, and I decided to start with the simplest Arduino I had around. And my plan was to try to see if I run into any limitations, I can try to take a step up or so, but just let's start baseline with a very basic type of thing. And so I started with the Arduino Uno R3 that many of you will be familiar with. Actually, at the time that I was doing this, I didn't have an Arduino R3 lying around, so I ended up using a, oh, you can hardly see it. Let me try to make it a little bit bigger here on the other camera. This is an Arduino Mini, Uno Mini, very cool little device. Actually, it comes in this very cool, beautiful box and everything. But basically, it is technically the same as a Uno R3. But as I will show you in a second, I had to upgrade several times for a variety of reasons to more sophisticated Arduinos in order to get my my prototype working in the way that I wanted to. So I want to talk a little bit about the different Arduinos that I've been trying for the prototypes and the reasons why I've been trying to make steps up in this prototype design. So first, what are all the Arduinos and Arduino likes I would say that I've been using? Actually quite a few. There are 8 in total that I've been experimenting with. There's the Arduino R3 that I just talked about. We got the Arduino R4 over here. Many of you really well know it's the recent introduction that has the big LED matrix display on it. It also runs on a more recent processor, a RAM processor. I've tried a little bit in the Maker series, something I use for quite a lot of projects with Arduino, but of course I got a older chip platform than the one that I just showed, the R4. I also tried the Arduino RP2040. So that's the platform they actually did together with Raspberry. So I got the same chip as some of the Raspberry chips. I also thought I'd try out the relatively new Arduino with ESP32 chip, so that's a bit of an atypical Arduino, but I was interested in its price-performance ratio. I ended up also trying like the fastest, most luxurious Arduino I think that you got around. It's the Portenta. I shall show a little bit of a bigger picture in a moment. The Portenta got actually a dual core processor, is very fast, is also very expensive. It goes I think way over 100 euros per unit. And then you can also have this nice extension board with it that you click it on and they get all the ports on, like hundreds and hundreds of ports. A pretty exciting device. But I'll tell you in a moment whether it was good for my project or not. And I tried two Arduino-like devices, which are teensy devices. And I'll tell you in a moment why I actually ended up looking at them and considering how to put them in. Now, I'm just showing you now all these devices, but why I was running into issues that I had to move away from my baseline design just using a Uno R3. Because we're only talking about playing back like 511 bits. I mean, what's the issue? Any platform could do that, I would think. Now, I was wrong there. And let me first go into the reason number one why I've been changing platforms a number of times over this project. And to do that, we have to look at the precise specifications of all the devices that I'm getting right here on the table. So 8 of them, and these are the specifications for all 8. So we see the processor, the architecture, and a couple of things. And the one that I want to draw your attention to is the amount of memory they got on board. And especially the amount of SRAM memory. And that varies quite a bit between 2 kilobytes and 8 megabytes, depending on the thing that you select. Now, why is that an important aspect here? Because the data that I'm using and I'm playing out, etc., is stored in an array in the C++ program. And I think that's kind of the straightforward way to do this. And then you would say an array again of 511 bits, what the point? And maybe a couple of arrays, also some arrows with predetermined errors, but that's not that much. But there are a couple of things going on there. And most importantly is that C++ is not very efficient in the way that it stores arrays on a device. What it does, even it's defined as an array of bits, it actually stores each bit as a byte. They probably thought it's a bit more convenient way to interpret it, but it's a huge waste of space. For every bit, we spend a full byte of storage room. And then also when I got a couple of different things, I ended up finding out when I'm running a number of sketches here that having like maybe something like 10 of these arrays of 511 bits, I ended up requiring 90 kilobyte of memory space to store them. And the thing is that the Arduino uses the SRAM memory basically to store that information. And then basically you will see on this table already that Arduinos like the R3 and R4 are basically too small. They cannot store the arrays here. Now you could try to store that somewhere else. There are some options like the PROGMEM identifier that allows you to change the memory or to use, I think, the flash memory in order to store arrays. But I couldn't get that working properly, and then I started to read like various posts on it, and then I started to read the official Arduino web pages, and they actually explain themselves that this is not totally reliable and does not always work. Well, so then I given up, and then I basically realized I needed an Arduino with sufficient SRAM memory to store my thing. So that's number one, basically having enough storage space to store the bit sequences on. Now the second thing has to do with speed. And like I said, speed is not a primary criterion, but we still want to have some decent playback speed. And throughout the prototyping stage, I found out that at some point things got really slowish. So I decided to do a more systematic type of speed test, just going down to a kind of very bare bone type of sketch that would be just playing out a very small array of numbers. And you see that code right over here. I just take like 8 different bits, a clock signal and a data type of signal, and I wrote a sketch that basically takes that bit out of the array, writes it to a digital pin, and then starts again, and without any delays. And let's just see how fast our different Arduino or Arduino-likes are in carrying out that code. Taking into mind that this is the fastest possible sketch to do such a thing. The real program will be more sophisticated, will write out more things, will have some UI things, so it will always be significantly slower. But this is the maximum rate that we could ideally get in any piece of program there. So now let's review the different Arduinos and Arduinos-like on the speed dimensions. So all of them I run exactly the same sketch that you see here, and I've just been measuring the clock output on an oscilloscope to determine the frequency of that clock. So what are we getting there? Now first of all, the Arduino R3 Mini, we get a clock rate, as you see here on the oscilloscope screen, of 58 kilohertz. And again, it will be much slower again if the code gets more sophisticated. That's not terribly fast. Moving on to the newer R4 Wi-Fi, it got an ARM processor on board. It's a brand new thing, just I think 6 months out or so. How does it do in terms of BER speed? We get 327 kilohertz clock rate, which is a bit better than the R3. I mean, okay, I can see that. It's still not fantastic, I would say. Now moving on to the Maker series, I've been using that quite a lot in projects in the past, and it has a bit of a more modern architecture than the R3, but not the ARM processor. Where does it end up? 156. Now that's not amazing either. Let's move to a little bit more modern platforms, the ARM type of platforms. Let's go to the Raspberry chip, the RP2040. That one clocks in at 450 kilohertz or so. So now we're making a bit more significant steps in speed. And then looking at the Nano ESP, and the ESP chip, as you might know, that is actually clocked pretty fast. So I was pretty excited to find out, how does that compare to more traditional type Arduinos, because a bit of an alien chip, the ESP for an Arduino, but they did recently make it, we got it here. Yeah, and then we're going up significantly, 724 kilohertz, and then going to this very expensive Portenta H7, over €100. Got a dual core processor there, one of them clocked at I think something like 500 megahertz, 400 and 500. Yeah, then we go a step up again, 1.6 megahertz speed. But then I also started to realize I still had a couple of other MCUs lying around, the Teensies, and the Teensies use pretty fast processors when you consider their price. So the Teensy 3.5 is already clocked at something like 500 megahertz, but it's actually, I think it's as expensive as a standard Uno, or even less to that. But with a very high clock speed, as a matter of fact. Now, do we see that when we run our sketch? Yeah, definitely. It runs at 900 kilohertz, which is already 20 times as fast as the R3, which comes for about the same price. So price-performance ratio is much better. I must say that I did see quite a little strange timing problems when I was running this little test. Maybe I did something wrong, and I'll show you in a moment when I did my test with the Teensy 4, I didn't have the similar problem, so it could be just me doing something strange or so, but I thought I should note that. So this Teensy 4, the most recent version, that one is clocked really at, I think 700 or 800, it was in one of the previous sheets. What do we get there? It's a whopping almost 6 megahertz of clock out. So just running a bare bone code, the Teensy 4.0 is really super fast. So actually I've been using a Teensy 4.1, that's the bigger chip here that I got in my hand, for doing this type of speed testing. Finally, in my prototype, you will find a Teensy 4.0. It's basically the same device, but with less I/O pins and a couple of other things. But processor and speed-wise, the 4.0 is as good as the 4.1 here, and the 4.0 was more than enough. And since I wanted to make my prototype, including the MCU, but also all the other hardware, for less than €50, I decided to use the 4.0 in my final device. Now, I do also need to talk a little bit about proper timing. And as I told you in the beginning of this video, I didn't care so much for timing, but a bit changed my mind over time when I actually saw how the timing was of my prototype. I mean, why didn't I care? Because I kind of know that these BER testers are not very critical basically if there's a bit of drift or unstable type of clock. They will just look at is the proper value coming in when the clock is coming and say yes or no, there's a bit error or not. But I got very annoyed when I noticed, you know, how poor my initial designs were timing wise. So I needed to dig into that a little bit again. And in order to dig into that, I again started by thinking, let's just run a bare bone code and let's try to get some understanding why my Arduinos apparently behave a bit differently than I had in mind when I was writing my code. And so what did that result in? So I took a code and I just took the Blink code. The Blink code that all of you know, that's the first code that all of us will basically upload into an Arduino here. And I took the Blink code, I just took out the delay parameter so I would make the loop as fast as possible, and I would measure on an oscilloscope the output, the LED of the output that I would put on and off with the Blink code. And you can see some of the results here on the screen, and some viewers might already have noticed I changed oscilloscope here. Actually, I'm looking at a Siglent oscilloscope here, not at a Roden and Swartz. The reason is that the Siglent oscilloscope has very nice histogram functions that are useful for this type of thing. So I'll be using the Siglent for this. So we can already see in the waveform that there's something going on with our clock code, and it's not entirely stable and repetitive. We see also in the statistics measurements that we see a minimum and a maximum that are pretty far apart, and we also see a little bit coming up with standard deviation. And then if we use this nice type of histogram, which is built into the Siglent oscilloscopes, if you let the code run for a very short time, you already see some deviation around what I would say the default clock frequency that we will be expecting or so. But if you let it run a little bit longer, we also get to see that sometimes it just goes to a clock which is only like half the speed or lower than the expected clock. So yeah, so this clock is not stable at all. Even if we just use this Blink sketch, you know, nothing special in terms of code, it already works a little bit different than you might expect. So I've been trying to understand a little, you know, what is the underlying reason for that, and I came to the following possible explanations that Arduino code doesn't exactly run timing-wise as you might expect it is. First of all, it's internal housekeeping of the MCU. So there are all types of things happening. This code is being compiled, and there might be all types of stuff running via interrupts or otherwise that is not so much part of your code, but nevertheless part of the housekeeping of Arduinos, and that changes the timing in ways you might not expect it. Then there might be asymmetries in the code. Well, there was no asymmetry in my Blink code that I just used. But if you write more advanced code, for example, you read out an array and then you start again and start reading it out from the beginning again, there will be an asymmetry. There will be a point in the code where you will be reading out the UI interface, for example, and there may be asymmetry in the code, and that can result in issues as well. What I also run into is that there is a significant execution time when you do I/O operations on the Arduino. In my original prototype, I actually had a potentiometer by which you could select different scenarios for BER testing. And you know, every once in a while, after he read the array like 5 times or so, he went to check if there was another value on the potentiometer. I found out that reading out this potentiometer takes as much as 100 microseconds. Now that might not be a long amount of time if you only do it once, like every minute or so. But if you do it like, you know, I don't know how many thousands times per second, then this really starts to be a problem. So I took out the potentiometer, the analog read altogether. But also the digital read and digital write takes some time. About 5 microseconds on the UNO type of boards, maybe a little bit less on the other boards. But this is still a significant time compared to the other type of operations of the Arduino in terms of code. And if sometimes, you know, you have to write an extra code to an external line, then it creates asymmetries, and again we run into that type of things. Now, so we have a number of different possible sources for timing problems, but then let's go and look at solutions for them. What could you do to make a device that does not suffer from this type of clock drift? Now, I kind of thought about the following different ways. First of all is introducing a lot of delays, a lot of knobs, you could say, in assembly code. Yeah, obviously, if you make delays, that there's only going to be like a clock of one hertz or so, 1 bit per second. I can make a device with very, very little drift, but it will get like totally slow. And actually in the beginning, I'm saying this as a joke, but in the beginning I'll be slowing down my devices a little bit with delay codes just to reduce the timing issues. But this is not a good route. You get slower and slower. Second thing is disable all the interrupts in case you write code without interrupts. So you get rid of the housekeeping things. That is advised by a number of websites. I played a little bit with that. It doesn't reduce all the timing problems, and on top of it, it can also create serious issues like non-responsive devices and not being able to reprogram your Arduino anymore, etc. So I didn't want to go too much down that route. A more elegant thing is to start to use interrupts yourself, to use hardware interrupts, and some of these hardware interrupts are timing interrupts, so you could tell it like every that many milliseconds I want to be a hardware interrupt to a particular part in the code that's going to write out a bit for me to a certain pin or so. Now that's a kind of an interesting route in itself. However, it does come with its own considerations, and one of them is that you really have to make sure that this hardware interrupt, this counter interrupt, only comes at the moment that you're really sure all the other code is ready. So kind of the worst case kind of things into the user interface and whatever, etc. Otherwise you would have an unreliable code. The other thing is that these hardware interrupts are completely different per processor platform. So you could completely specialize yourself in doing that for the old Uno type of the RV platform, the ETA Mega controller. But then if you would migrate to one of the others, like the ARM chip or the 2040 chips, you have to start from the beginning. You have completely different libraries, completely different interrupt structures, etc. You have to start from scratch, have to investigate them, see what they can do, how you can use them. So it's not going to be portable across devices anymore at all. So I've been not going down that route. Another rather elegant solution would be really to go to a real-time operating system. Maybe one day in my life I'll dig into that, but I have little experience with that right now, so I didn't do so. The final thing that I opted for is hardware-based timing. This is probably also a bit of more of my background. I'm more a hardware guy than a software guy. So I finally figured out, let's make a piece of hardware that determines the timing, and let's make this all independent of the aspects of the software. So let me explain a little bit with the hardware solution that I eventually designed for this. Now I'm calling it TikTok, like the TikTok from the Intel processors, of course. That's something different. But anyway, my click clock is at TikTok is as follows. I take a clock signal. I will call it here the inverted clock signal for a moment. And that clock signal has a upgoing edge and a downgoing edge. And on the downgoing edge, basically, it is telling my microcontroller, prepare a new bit value, prepare a new data value. Then basically on the upgoing clock signal, I'm giving a clock to a flip-flop memory, and the flip-flop memory actually takes the value that comes out of the microcontroller and then clocks it out to its real outputs. So just as long as we make sure that this positive edge comes after the microcontroller is ready putting the right value there, then the whole timing is basically the flip-flop timing. And the flip-flop timing can be perfect. That is really the clock signal that I got here. So it will clock out all the different signals at precisely the right moment, but also all the signals at the same time. So you don't have like with digital read, at first you do digital read 1, then digital read to another port, then digital read to a third port or whatever. No, with this flip-flop memory, everything comes out exactly at the same point in time. And finally, I'm also using my clock signal as the clock out for the user. That was one of the design requirements. But then I inverted, and that gives the regular clock out. That's why I had a negative clock. And so I can just use my own clock signal for this exercise, and I'll show you in a moment that my device both has an internal clock and an external clock possibility here. Now let's go and take a look at the final prototype. How does it look like? And there were quite a couple of iterations. I'm going to show you a picture of the lab, and I'm actually doing some experiments here with my device, and I'm testing it actually already here with a bit error tester. That is the big device you see at the top of the screen. That's an Anritzo MD3700A, I believe. So here we already see it's properly working. I'm going to do later some videos where I actually use it in action. And this is one of the later prototypes, already pretty close to completion, I would say. But before I got to this more mature prototype, I must admit that I built quite a couple of other prototypes in order to get to this point. So here you see a picture where you see a little bit of the work in progress with different versions and different stuff going on breadboards before I got anything close to it. But it was an exercise that I learned quite a bit with, so it was fun to do in a way. Now, this is how the prototype looks from the outside. It's over here, and I'm also showing you a bigger picture on the screen. So we got the actual outputs. I think I'm going to turn it to the other screen for a moment. Yeah, so we got all the different outputs, so the real signal, the modified signal, the clock output, the frame start output, the bit error output. The clock input is on the back. Actually, right now it's missing in this version. I'll tell you in a moment why. We got a user interface that we can basically bring it through different scenarios by pushing a button up and down, and then we see on the screen the different scenarios, talk about in a moment, and we can select either an internal clock of 100 kilohertz or an external clock which is not connected right now. And then if we move to the inside of the device, it looks pretty straightforward. It's not a very complicated design. You probably already recognize the MCU. You see a crystal, so 1 megahertz crystal that we divide by 10. That's the chip right above it. And we see a couple of other chips which are basically the flip-flop memory and a buffer stage. And you might also notice at the left bottom there is an additional header there. Let's make it a little bit bigger here. And that additional header is a debug header. That can be used to connect the prototype right away to a digital oscilloscope, digital lines of oscilloscope, to do some further analysis how the code internally is running. And the reason why I built a connector like this, I mean, it's a bit brutal, but I just wanted to be a very robust type of thing rather than elegant. Because I wanted to build in a way that I could directly connect the digital port interface to an oscilloscope without having to put all the wires there one by one. So what I finally built is that I can use the Roden and Swart probe with all the 8 lines and plug it directly into the device like that without having to configure each port separately. 8 ports are enough, so I don't need 2 of them, where I would have 16 of them. But at the same time, I thought it would also be nice if I can use my other oscilloscope. So I also got here the interface of the Siglent oscilloscope. And actually, it was not too hard to make them compatible with both. The only thing is that you have to put the Siglent interface kind of upside down, because it got the pins and the ground row just in the opposite way. But it works perfectly. Actually, the Siglent interface got 2 rows of 10 pins, but the outer pins are ground and are not used in my design, so it just stays compatible. There's just a space that you can plug it in. But this we basically got here for debugging purposes. Now I want to show to you the circuit design itself and quickly guide you through it. I will be posting this as well, should anybody want to try to build it him or herself. So it's a pretty straightforward design in the end, where we got basically a clock signal which comes here from an internal crystal that we're dividing by 10, so the 1 megahertz actually becomes 100 kilohertz, or we got a switch here allowing us to input a TTL clock signal from the outside world, and that's actually a maximum of approximately 1.3 megahertz. And if we go above that value, the device doesn't work properly anymore, because then the code cannot keep up anymore, but we will have a red alarm light going on warning the user for a too high clock signal. Now, what do we do with the clock signal? Like basically what I told you in some of the previous sheets, we bring it into the microcontroller so it knows when it has to start to calculate a new code. Actually, we got a resistance divider here because the microcontroller runs at 3.3 volts and the TTL level is 5 volts. So we don't want to destroy our device, right? So we got a frequency, a voltage divider. We also bring the clock signal here into the flip-flop here, which is a 74 LS273. So that's an octal flip-flop with a common clock signal, and this one is sensitive basically to positive clock edges, where I program my microcontroller to be sensitive to negative clock edges. This is reacting to the positive clock edges, so we got the tick and the tock basically, and then basically the signals come out here after clocked, and I bring them once more through a bus that is inverting them, and then we got the output signals. I've been using this bus on all my prototypes here, this buffer here, and I like it. That's why it is there. You might throw it out if you strongly wish to. But I needed anyway to invert already the clock signal here, so I got the chip anyway. Using, by the way, only 4 of the memory positions in the flip-flop. There are 8 of them, but 4 of them I don't need, so I'm not using them. User interface, very simple. There's a switch here that allows us to go scenario up, scenario down. I think you just saw it. There are a couple of pull-up resistors. We can actually also leave the pull-up resistors out because in the TNZ and a couple of Arduinos as well, you can software program an input to be pull up or pull down or have other characteristics. But then it does become a little bit of platform dependent, of course. So I've drawn them in here. I got the well-known SSD 1306 display. Probably a lot of you know it. It's this almost 1-inch diagonal small OLED display. One of the reasons, by the way, I'm working with this display now a lot is that you got multiple libraries that all work pretty well. And my experience is that once you got it running and the library running for one Arduino, actually you might find that another Arduino like the 2040 really does not want to run that library. So at least you can switch to another library and get things going. You have to investigate a little bit a new library and to do the same type of things, but you got a bit of flexibility if your display chip has multiple libraries that support it. And then we're basically almost there. There's the arrow LED. I just choose a high efficiency LED that only draws like 2 milliamps, so we can directly hook it up to the output port, so we don't need an additional buffer here or chip. Just trying to reduce the count of components and soldering work here. And finally here we got on the right the debug output. So the debug outputs basically include like the NP9 signals and the frame signals coming from the Arduino chip. But of course they're going to be different than the final output because that is before the timing with the flip-flop stuff. So we can actually look at the timing differences this way via the debug interface. And there's also going to be a couple of specific debug signals, and they're called loop 1 and loop 2 and debug right. And these are additional signals that are generated so you can do some debugging at the interface in terms of the wait loops with the clock if all of your code behaves in the way that you thought it should. So pretty straightforward, not that difficult to build, and everything works, I think, as it should. Now, also showing you a little bit of the different scenarios. I already talked about different scenarios that you can select for bit error testing. So these scenarios can have like built-in errors at predetermined conditions. I mean, I just decided myself where the errors are. I made a table and I said, okay, I want to have an error at the 175 bit or so that comes along for a certain pattern, etc. So there are kind of 16, 17 values that you can browse through via the scenario interface, and the first 12, 13 or so are kind of regular scenarios. The first one is anyway just send the proper code out. So the modified output exactly has the same as the unmodified output. It's a proper NP9 code. So you can use to calibrate your device without having to switch connector from one to the other. And by calibrate I mean the BER tester. The BER tester needs some proper code before it can start to analyze codes with errors. So it's easy if you don't have to switch connector to do that. Then we got a couple of scenarios where we simply would have 1, 2 or 5 errors that would come in every sequence of 511 bits in the NP9 code. So each of them goes associated with a certain bit error rate. So if you would have one error over 511, then I think you got the BER of 0.049 9%. So that is kind of a repeating type of error code. What I also wanted to see and be able to test a little bit how bit error testers deal with more real life type of signals, where not every sequence has exactly the same error coming in, but there might be one sequence without error, there might be one sequence with quite a couple of errors, then one with just only a few errors, etc. So what I did is a mechanism by which you have 4 different frames, and these frames could have different errors in it or not. And that is what you see, for example, at scenario number 3 and scenario number 5. These are scenarios that play around a little bit with different type of frames with having different error rates. Scenario L11, that's already quite a lot of error. We got a bit error rate of 5%, so 5% of the errors are having an issue. Scenario 12 is even almost 10% of all the bits have an issue. Scenario 13 is a bit of a special scenario because we got quite a lot of errors, but these errors are also clustered within 64 bits. And I do this because some bit error testers tell us that they're not able to deal with that many errors if they come close together. So we can test a little bit how they actually deal with such a thing. And then there's also more for testing purposes, something where all the outputs are 1, all the outputs are 0, where all the outputs are just alternating. And then it finally is the debug mode. And actually you can do debugging in all the different modes of the device, but the special thing about this debug mode, which is technically almost the same as scenario 4, that it also activates the debug pins that are in the wait loop. So then we can really see how the microcontroller is waiting for the tick-tock clock signals, and if we have enough cycli there to properly relate to that, and whether the system that detects if there's an error of too high a clock signal, external clock signal, and that properly inform the user that there's something wrong there. Why did I build a separate scenario for this and not that you can do that in whatever scenario is running? The reason is that to have additional outputs very quickly going on and off within these loop states also will cost you some time. So the overall maximum clock speed of the device will go down from approximately 1.3 megahertz to approximately 0.8 megahertz. So it is going to be a little bit smaller. Not terribly slower, but a little bit slower. But I decided to make it a separate mode for that reason. And finally, if you click to position number 17, I think it should be 18. We got 2 17s here. Something must be wrong in my table. Then you just get the splash screen and the firmware version and some other information about the device. Okay, it's already getting a little bit late, but I still would like to do some field experiments and see how the signals out of our PN9 generator look on the oscilloscope. So let's just start to look at the output signal when we start in a basic scenario with a clean output, and it's pretty straightforward. On channel C1 we see the PN9 code, 511-bit PN9 code coming out of the device. On channel 2 we see the modified signal, but since this modified signal is also the clean signal, it's the same thing. And C4 here we see the frame start. So this is when every time when 511-bit frame of pseudo-random bits repeat itself. And finally on the clock output, which is right over here on the device, we see the clock, and the clock right now is about 100 kilohertz, and that is the built-in clock into the crystal into device. It's a 1 megahertz crystal divided by 10. So that's more or less what we will be expecting here. I'm just getting this out of the way here, and we'll have the clock signal also down here at the bottom here. Now, so the basic purpose is that we can introduce some errors into the signal. So let's go to scenario number 1. And scenario 1 is a scenario where 1 out of 4 frames, as we see on the little graph here, has an error. And yeah, we see that error right away, rather early in the frame, popping up and down. Next scenario got an error every other frame, every 2 frames. So we see actually the error popping up a little bit more frequently. And then we have a scenario here where every frame we exactly got the same error coming in. So we can see the error basically by comparing the clean code with the modified code. But an easy way, of course, on an oscilloscope also to do that is you make use of the mask channels. So I'm turning on my mask channel here, and the mask channel is basically just taking channel 2 minus channel 1. So a positive peak here, there's that channel 1 is a 1 versus channel 1 was a 0, and the other way around we would have seen a negative peak here. So here in this way we can easily see where all the errors are. And if I would zoom out on the time base a little bit, I see, yeah, there's only one error every frame here. I see every frame start, and about the same amount of times I see the errors coming in. But we can of course go to a scenario here which has much more errors here. So we got a scenario here where some of the errors are different per frame where they are. Let's go to a scenario here. This one has considerably more errors over here. And we can even go to scenarios with plenty full of errors. Let's see here. 50 errors per frame. And this is actually the same 50 errors every frame, so this is a stable thing. And so we got all types of interesting scenarios here where we can have errors which are depending on the frame or not, etc., which can be visualized. So yeah, so in so far we can see a little bit how the error handling of the device is going on. I think I touched this button. Yeah. Okay. So this is as we would expect it. We see the errors coming in. Then we can also look a little bit at the debug interface, and before doing so I'll just try the external clock. So I have prepared here a signal generator, and it just creates a block signal with TTL properties. So I'll change to the external generator. Yeah, and we see here the clock signal now is turning to 500 kilohertz. That is what we set this device to. I'll make it a little bit bigger here. And we're still in the scenario where the errors are different per frame. We see a little bit of a slow start here, the slew rate. Well, that's okay with TTL signals, and we just bring that into the scope without any specific impedance matching or so. Again, the reason why I'm using TTL signals is because the BER testers I want to try later on are TTL. I'm still thinking about adding some extra outputs here that are buffered and a nice 50 ohm output signal, so we can also use it with scopes a bit better. But it's not a big deal. The signal is clean enough as it is for this purpose. So now we're running on half a megahertz from the external source, and I would like to go and show you the debug mode, how that works. So to do so, I'll go to the debug. Actually, I'll go one more than the debug menu. And the debug interface, that is via the digital lines of the scope that goes into the probe that I showed you before, the back of the device. So to see that, let's turn off the math channel. That's going to be a bit out of in the way. And I'm going to turn on the logic signal of the scope. Now we got all the debug signals coming in here. And what do we see here? We see actually just under channel 1, the MP9 code, we see the digital version that was the source for the MP9 code. On the channel 2, we see the digital signal that was the original source, and on the channel 4, we see the original digital signal that was the source for the frame start. But if I zoom that out a little bit, you will already see it's not super stable. It's jumping up and down a little bit. And this is not happening for the digital signal of the clock. And this totally makes sense. This is why we have the hardware circuit for correcting jitter, because what we see here actually is the jitter of the Arduino, the teensy. And that timing is properly corrected by the circuit with the flip-flops here. So the flip-flop have a super steady timing that runs exactly in sync with the clock. But actually the signal as it comes out of the Arduino, can we see here, that is the signal that is having some jitter here. So this is basically telling us that the clock circuit is, or the hardware circuit is just doing what it needs to do. Now, what is peculiar or interesting also about the real debug interface, and I'll turn it on now. There we go. There we got these little things over here. Do you see these little spikes here? So what we see is basically, we see the wait loops. Let me make it a little bit bigger so we can investigate them a little bit. Again, we see the timing problems a little bit more. And so here we can see the wait loops. And it is these wait loops that basically take care that every time the Arduino is waiting a little bit to the right moment to bring its values into the flip-flops, then the flip-flops are clocked out exactly via the steady clock. And then again, the Arduino has to wait for a moment until it can properly deliver its data. And it is the proper right moment. So basically what we just see here is the wait state here of the device. And if we go to a lower clock frequency, then we would see that we have many more wait states. While if we go to a higher clock frequency, and we will of course see that every time we have fewer wait states, and then he already has to deliver the next value. So 700 kilohertz is still kind of going fine. 800 megahertz is still going fine. Sometimes there's just one single wait state. 900 is still kind of going okay, but we're at the edge here. So sometimes there's just one single wait state to wait until he has to deliver. And if we go further up, then we see the arrow light on the device going up, and that is basically telling us that he cannot longer keep up. And we can also see that on the scope here, because sometimes there is simply no wait state anymore. So this debug interface can be used basically to investigate a little bit better basically to what speed the device can run. Now in the debug mode, as you can see, we can go to 900 megahertz maximum. However, if we stay in a regular state, we can go actually faster, and we go to 1.2, 1.3 megahertz is still running well without the indicator going on. Everything is still fine. And at 1.4 megahertz only is not working. What is the reason why the device is faster in regular mode than in debug mode? Well, the thing is basically, and I'm bringing you back to the debug mode here. In order to run the debug mode, you have to use a write pin on the Arduino several times. And the write pin takes quite a bit of time, and that basically makes the algorithm a little bit slower. And so in order to be able to see this information externally, you have to go to a slower algorithm, and so the maximum speed is slower. But anyway, altogether the device seems to be doing exactly what it needs to do. And in a later video, of course, I'm going to connect this up to a BER tester rather than only an oscilloscope, and we can investigate a little bit more. Okay, that was it for today's episode. I hope I give you some nice ideas and inspiration to also build your own devices and maybe experiment with this device. Again, I'm going to leave the design as well as the software code as publicly available in a GitHub that I will be linking to. I hope you like this episode, and I'm going to be planning one more episode in this series where we're actually going to do real bit error testing with the test generator we now generated, and looking at a number of different scenarios. Thanks for watching. Don't forget to like the channel if you enjoyed this, and see you next time.